Hello and welcome. Today we're doing a question from LeetCode called Combination Sum 3. It is a medium. Now, before jumping into this problem, we've already done combinations and combination sum 1 and combination sum 2. So before doing this problem, I highly recommend watching either of those videos, specifically combinations or combination sum 2, and giving this one a shot. They're very, very similar. If you're able to do those, you'll be able to get very close to, if not get the exact solution for this problem. So give this one a try, and I'm going to assume you've already given it a shot before moving forward. Now for this problem, we want to find all valid combinations of k numbers that sum up to n, such that the following conditions are true. Only numbers 1 through 9 are used, and each number is used at most once. Return a list of all possible valid combinations. The list must not contain the same combination twice, and the combinations may be returned in any order. So again, this is a combinations problem. We want to use numbers 1 through 9 inclusive. Each number may only be used once, and we want to find all combinations size k that sum up to n. So example 1, we have k being 3 and n being 7. So the only combination size 3 that sums to 7 is with 1, 2, and 4. And with example 2, again, k is 3, n is 9 this time. So these are the combinations that meet the criteria. And example 3, k is 4 and n is 1. No combination of size 4 actually sums up to 1, so we don't return anything. And we have some constraints over here. We've done a lot of combination problems before, so we know exactly how this works. But regardless, we're always going to start with examples to build up our logic and really visualize what our solution should do. So say k is 2 and n is 5. I want to find all combinations size 2 that sum up to 5. And I can use numbers 1 through 9 inclusive. But of course, over here, I don't really need to go past 5, right? I need a size 2. So I'm basically only considering numbers 1 through 4. Now, if I want to make combinations, what do? I always pick that first number to start off with. So right now, I'm picking 1 as my combination. This is my current combination. And how does this affect n and k? Well, with this, now k only needs 1 more to go. I've already used 1 element. We need 2 in total. And n now needs to be 4. I only need a sum of 4 now. So since I want to add numbers to my current combination, what do? I only have the numbers after my current index as possibilities to add on to my combinations. And we always do this to avoid duplicate combinations. So something I could do is 1 and 2. Now this sums up to 3. It's not the 5 we want, but since this does meet the requirement of k, we can't add more numbers to make our sum greater, which means we want to swap out the 2 for something else. And we had all of these numbers available to us, so now we're going to swap it off with a 3. A 1 and 3 still doesn't sum up to 5. We continue swapping it out. 1 and 4. This does sum to 5, so we're going to append this to our resulting array, because at this point, k has gone to 0, and n has also gone to 0. So result now holds 1 and 4. So now we've explored every single possible option with 1. We are done with that, and we're no longer going to consider it. So now for our next combination, we start off with 2. At this point, k equals 1 and n equals 3, so we can still add more elements to this. Now, what elements can I add? I can only add elements on the index after me. I can't go before me because that's going to create a 2, 1, which we've already seen before, right? We always do this. We can only start at an index after the number we just used. So now it's going to be 2, 3. Over here, k equals 0. There are no more elements we can add here. And n also equals 0, right? This has a total of 5, so we don't need any more numbers to reach that sum. So we're going to add this to our result. Now that we've added this in, there's no point in switching this out for a greater number since that's going to go over our sum. So we're going to now choose another starting number. So we start off with 3 at this point, and this puts us with k being 1 and n being 2. Now, we are only looping through from indices after us, so we know we're going to start from 4 onwards. But since we're only looking for a 2, it only makes sense to go up until 2. If we go to anything past 2, we're going to overshoot our sum, right? So technically, we're ranging from 4 up until 2, and that doesn't match up, right? We're already past where we want it to end, so we know we don't really need to go down this path at all. So in order to solve this problem, what we're going to do is make combinations like usual. And what that entails is picking a number and doing a depth first search. So recursively, we're going to keep looping through all the available numbers to us and keep adding on to our current combination up until k equals 0 and n equals 0, in which case we will add our current combination to result. Once we explore all valid possible combinations, we just return. So we're going to go ahead and code all of this up, and if it's confusing at all, don't worry, we're going to walk through a complete Example. To code this up, the first thing I'm going to do is initialize my resulting array. This is going to be empty and going to hold all the valid combinations of size k that sum up to n. Now I want to define a recursive function that makes all my combinations. I'm going to define that within this function right here, just because that way I don't have to pass in result and k and n every single time. It just makes for cleaner code. So I'm going to define combination, my recursive function within this, and what am I going to pass in? I know I want to keep track of the current combinations that I'm building, so I'm going to call that current. I'm passing in a k, an n, and a start. Now this is going to be my starting index, right? If I start over here for my new combinations, I'm making combinations from here onward, I know I can only add elements past that starting point. So I'm going to keep incrementing this every time I call this function. Now with a recursive function, there are two things to keep in mind. One is the base case, when do I stop? And the second is the recursive case. When do I keep calling this function? For the base case, when do we stop our function? Well, that's when both k and n equals 0, and we'll append our current combination to result. So if k equals 0 and n equals 0, result.append current. That is what we're going to do, and we're just going to return out of here. Now, when else would we need to stop? Over here, when n was 2, we stopped once we hit 0. We wouldn't keep adding elements once k was 0. So this is checking once both are 0, but if k is less than equal to 0, we also want to return. We don't want to keep appending elements. If this is not the case, we still have room to add more elements. Now, how do we know what elements to add to our combination? We're going to loop through all the available numbers to us and try adding them all to our current combination. So for I in a range, we're going to start from our starting point. And what do we go up until? Well, we know we're only allowed to use numbers 1 through 9. So we're going to do 10 because it's not inclusive. But what if in our current combination that we are building, we have, say, n being 4. We only have 4 left. It doesn't make sense to loop through up until 10. We can just stop at 4. So I'm actually going to do a minimum on 10 and n plus 1, because again, this is not inclusive, so we need to do n plus 1. And why am I doing the minimum with 10? Well, what if our n is 60, right? We don't want to go all the way to 60. We want to stop at 10. So whatever's the smallest value, either 10, or if we have a value less than 10, we want to stop there. So we're going to loop through for all of these elements, and we're just going to call combination again. So we're going to call combination again with our current array plus the I that we are on. K is going to be k minus 1 because we've now added on this element. N is going to be n minus the I that we're using. And start is going to be I plus 1. And in the end, we just have to return. So I'm going to go ahead and call this function now. We're calling combinations with a current array, initializing that to start off with an empty current combination. K is just going to be k, n is going to be n, and start is going to be 1. We want to start off with 1 through 9 inclusive. After we finish calling this, we just return our result. So let's go ahead and submit this, and it is accepted. Now, before leaving, we're going to do a complete walkthrough of our code line by line to make sure we really know exactly what's happening and just visualize every single step. So say I have the following example, k is 2 and n is 4. So going through this, right, the first thing I do is initialize result to be empty. I define my function over here and I call it. So I'm calling combination with the current being empty, k being 2, which is the k we have, n being 4, and start being 1. So we're in this function now, we just called it, and we make a check. K is not 0, so it doesn't matter what n is, this already fails. We don't go in this if. We check over here, k is not less than equal to 0 either. So now we're going to loop through our possibilities. We're going to start off with I being start, which is 1. So we make this call, we're calling combination again with our current array, which is empty, with I passed in. So we're passing in 1. So the empty array plus an array of just 1 is just going to be 1 by itself. K minus 1, so that's going to be 2 minus 1, which is 1. N minus I, so that's going to be 4 minus the element we're using, that's going to be 3. That's our new sum that we're looking for. And I plus 1, so that's going to be the starting index of 2. So we go back in this function, k is not 0. K is also not less than equal to 0, so we're in here again. And this time we're starting off with I being 2. This makes sense, right? We don't want to use that 1 again. We're avoiding duplicates this way. So now that I is 2, we call this function again. And this time we're passing in current plus I, which is 2. So that becomes an array of 1, 2. The new k is going to be 0. The new n is 1. And the new start is 3. So we go back in this function. k is equal to 0, but n is not 0, so we can't append our current array to result. So we go in here, k is less than equal to 0, and of course we haven't met our condition. If we had and k was also 0, we would have just appended our current combination to result. So since we haven't met it, even if we were to add another value to meet that condition, we would have gone past the k size that we want. So we're going to return out of here and return to our caller. This combination is no longer going to work. So we go back in this function where we just finished making this call with I being 2. We go back in this for loop, and we have to loop through between 10 and n plus 1. N was 3, so we're looping through between the minimum of 10 and 4, which is 4, and it's not inclusive, so we can go up until 3. So now I is going to be 3, and we make this call again. So adding an array of I, which is 3, to our current array puts us at 1 and 3. K minus 1 is now 0. N minus I is now 0, and I plus 1 is 4. So we go back in this loop, and now both of these are true. K is 0 and N is 0, so we're going to append our current array to result. Once we do that, we return. So we go back in this function, right? We just finished making a call with I being 3, but this time we can't go in our for loop because we've already hit our endpoint. So we return out of here as well, and we're back in our original function. So we just finished making a call with I being 1. Now we're going to change this to I being 2. So we're back in this for loop, and we call this again with I being 2. So this time we call this with current being just 2, k being 1, n being 2, and start being 3. This if condition does not match, neither does this. And once we go in this for loop, we have to start at index 3, but we also end at the minimum between 10 and 3. So that's going to be 3. If we start at 3 and also end at 3, but we can't include 3, we can't actually go in this for loop. There are no indices to iterate over, and we just return. So we go back to our caller and bump this up to 3. So this time we're calling this with current being 3, k being 1, n being 1, and start being 4. And the same thing is going to happen again, right? We don't go into this if condition, and we don't go into this. And we have to start with index being 4, but we end with index being 2. That's not going to work, so we exit out of here, we return, and we go back to our caller. We're going to make our last call now, so we're going to go to 4, because remember, the end over here was n plus 1, so we're looping through up until 5 exclusive. So this is our last call being 4. We call this again. So in here, k is not 0, so we don't go in here. N is 0, but k isn't, so we can't append anything to result. K is not less than equal to 0, and we try to loop through. Starting from 5, but ending at 1. Again, this is not going to work, so we exit out of here and return to our caller. At this point, we're in our original caller again. We just finished going through every single iteration possible, and we return. So we exit out of this and just return our result, which stores all combinations size 2 that sum up to 4, which is just going to be the combination of 1 and 3. Now, talking about space and time complexity. For time, we're going to be making all combinations from 1 to 9 of size k. So if you're familiar with combinatorics, this is going to be 9 choose k. However, we also know that k is bound between 2 and 9. So even if we were to take the worst option, if we did 9 choose 4, we're still bound by a total of approximately 126 combinations. So we can actually argue for both space and time. This is going to be constant. We know the maximum amount of combinations we can make for any n or k that we're given. So we can say that is O of 1 constant for both, but if we do want to use a more generic approach, we can say that this is going to be 9 choose k. And for space, our recursive call stack is only going to go as far down as the number of elements we want to store. If we are past that k, we don't want to try to add any more elements and make more recursive calls because we've already overshot. So our space is going to be O of k, and time is going to be 9 choose k. But again, we can argue both could be constant. So we just went ahead and did combination sum 3. If you have any questions whatsoever, of course, let me know down below. I will answer all of them. If this video was helpful, like, comment, and subscribe. It really supports the channel. And as always, I will see you in the next one.